All right, howdy folks. Welcome again to Professor Carbon. In this video, we're going to go over an arrow pushing mechanism for the reaction shown here. I would generally classify this material as the kind of content that students might be exposed to when they're first learning about allylic cations or alcohol and alkene functionalization reactions. In case you're new to Professor Carbon, what I'd encourage you to do is to find one of our video playlists that interests you the most. So we have them broken down into things like arrow pushing mechanisms, synthesis questions, general reaction knowledge, and we also have them categorized by the functional group or content of interest, such as ketones or aromatics or esters and carboxylic acids. And if you're just scrolling through the channel, you'll be able to find our content listed up here by functional group, and the little explosion diagram over here will tell you what kind of reaction it is. All right, the other thing that's central to this channel is that I encourage students when experiencing or trying to solve these problems for the first time to actually pause these videos and take a few minutes to try to work through this problem all on their own, instead of just listening to the answer that I'll provide here in a moment. So please pause the video and try to solve this problem all on your own. Okay, now that you're coming back, hopefully with a problem or a potential solution in hand, let's just talk through this reaction. For those of you that may not know this, this is the molecule geraniol. And it's a naturally occurring alcohol. It's a isoprene or terpene molecule, and it actually contains 10 carbons, and so it has 2 of these so-called isoprene units in them. It's a very common biological building block to make a number of complex molecules, including steroids. And so ultimately steroids are derived from molecules like geraniol. In this particular reaction, we're going to produce limonene. And limonene is also a naturally occurring molecule. As you may guess from its name lime, it actually is the essence of citrus peels. And so you typically, if you scratch a citrus, you get on the outside, you get a little spray of oil that kind of smells very pungent. Part of that is limonene. And so this is a reaction that definitely occurs naturally, probably not with sulfuric acid, but under acidic conditions in a biochemical environment. So in this particular reaction, whenever kind of looking at a mechanism for the first time, what I try to encourage students to do is to look at the fragments that are around and see which kinds of bonds need to be made or broken. In this particular case, our starting material has an alcohol in it, and there's definitely no alcohol in the product. So at some point, we're going to have to remove that alcohol. We're going to have to make a new carbon-carbon bond to form this ring. And one thing that can really help with that is to start numbering our carbons. And occasionally it's confusing how to do that, but in this particular case, I think we have these 2 methyls out here, and that looks to me to be these 2 groups out here. And so maybe if I start numbering from this carbon, I can go 1, 2, 3, 4, 5, and then there should be a methyl 6 on carbon 5, 7, 8. And let's just see if that works here. So 1, 2, now we have a choice to make which way to go around the ring. So let's just try one of them. 3, 4, 5. Oh, and that's convenient because then methyl 6 is also on that same spot, right? So over here we have the methyl on the carbon 5-6 bond. We have that same group right here. And so that's a good indication that our kind of math is working out quite nicely. So then 7 and 8, here we go. All right, so that works out. Then we just have to make a bond between carbon 2 to carbon 7 or 8, sorry, over here. So it would be that bond. And then we're going to have to move this double bond somehow. So in any event, a lot of stuff is going to go on. But I think now that we have it mapped out, hopefully we have a better idea of what that might look like. Also, one other thing I always encourage students to do is to pay attention to what kind of reagent you have in these reactions. And in this particular reaction, we have H2SO4, so sulfuric acid. And I'm going to abbreviate that as H+. I know that there's differing philosophies on whether it's okay to represent H+ all by itself or not. I'm comfortable with it as long as we agree that there's no such thing as just H+. It's always balanced out by a counter ion. Here, the counter ion would be HSO4 minus throughout. And so I'm just going to keep my arrow pushing simple, by being comfortable using H+, and then ultimately we'll have H+ kind of fall off into the vacuum. Now, strong acids like sulfuric acid can do a number of things. So many times we've seen them take something like an alcohol plus H+, and we can, protonate that alcohol to make some good leaving groups. So that would be something that we'd want to consider. We may also have seen alkenes attack H+ to generate carbocations. And in this particular molecule, we have both functional groups, right? Draniol is both an alcohol, but it also has not one, but two double bonds in it. And so this leads to some issues of chemoselectivity that we might want to discuss. Generally, I think carbocations are considered to be higher in energy than the protonated alcohols. And so generally, hydronium ion is thought to have a pK of about -2. So H3O plus in equilibrium with H++ water. So this would be the acid, may have a pKa of -2. For those of you that think water has a pKa of 16, you're correct. And I'll remind you that that's a slightly different equilibrium. -2 is a reasonable pKa. That's certainly something that puts all of our strong acids like HCl or sulfuric acid have lower pKas than that, so they'll for sure protonate water and make H3O+. And so hopefully that's something that we're definitely familiar with. So if I had my choice, I would tend to start with the OH functional group instead of the alkene functional group, just because I've built up that kind of chemical intuition, and I generally consider carbocations to be more reactive or higher energy than their corresponding protonated alcohol counterparts. So let's start with that here with draniol. Used to draw draniol so much as a grad student, so it's kind of bringing back memories here. All right, H+, gonna protonate that. Cool. And let me see here. What do protonated alcohols do? Well, they can leave, so they're reasonable leaving groups. So let's do that. Now, some of you might be a little nervous here because now I have a primary carbocation, and those primary carbocations are a little bit rough to form. But some of you might also be experts and recognize that we have this double bond next door. So this is an allylic carbocation, and it has a nice resonance structure. With this carbocation. And so this is now a tertiary carbocation. And so even though it might seem a little bit high energy to form this primary carbocation, because it's allylic, it's probably all right to make, especially because the other half of that allylic side is tertiary. All right, now if we look back at our product here, I'm just going to scroll up slowly. This product, we have to make that ring between the carbon 2 position and the carbon 8 position. And so some of us may wish to do that just by having this alkene here that we had in our first intermediate. We could just imagine this attack that I'm drawing here in yellow. The only problem with that is that this double bond here is an E-alkene. And if we look at it up here at the top, it is definitely a cis-alkene. Or if you're more comfortable with Z, since it's tri-substituted. All right, so we have to do something to account for that. And what I'm going to do here is pretend that this now that's drawn as a single bond can just kind of flip over. And often we don't draw rotations as part of our arrow pushing mechanism, but in this case, because we have to go from that E-alkene to the Z-alkene, I thought it would be a good idea to include a little bit of an extra step. Oops, what am I drawing? And now if we take our resonance structure back, using my resonance arrow again, now I can go back to that other primary carbocation resonance structure that we had up here. And of course, that's the least stable of the two possible resonance structures if we had to consider them. But there is significant carbocationic character on that carbon, and also the least stable tends to be the most reactive. And so perhaps then we can take this alkene and have it attack there. Now I'm just going to add some numbers in here to make sure that we have our system correct. Make sure that we don't goof at all drawing the product. And by the way, that's something I encourage you to do as well. It'll help you from making an accidental mistake. So let me just number here. So I've got 1, 2, 3, 4, 5. So that means I need to have my 6 carbon coming off of there. And I'm going to need my 5, 4, or 5, 7 double bond. 7, 8. So I think that's all okay. And now carbocations can do a number of things. And so often I encourage students to think about all these anytime they draw a carbocation, really. But carbocations can capture nucleophiles. So that's what this one did up here, right? So if we label the alkene, this would be a nucleophilic partner, and that carbocation is going to be our electrophilic partner. So we can capture carbocations with nucleophiles. We can have carbocation rearrangements, or we can lose an H plus nearby. And when we do that, you'll end up reforming an alkene. And in this particular case, what we're going to do is have that H plus just fall off like so. And so that would generate then for us the product. Limonene. And then if we want to go back and consider, we're not actually having H plus fall off into a vacuum, we could kind of imagine what's really going on here. And most likely the best base in this whole process is going to be H2O that we generated. And so we can add that together here, that H2O plus H plus is going to generate H3O plus. And overall, that means that the sulfuric acid is used in the reaction because we don't get a free H plus back to go back on the bisulfate anion. Instead, the water here probably actually absorbs that. And that helps explain why sulfuric acid is a strong dehydrating agent, is because we're protonating water as we form it. And that helps make it so that there's minimal amounts of actual water around because most of it is shifted forward to H3O+. All right, so hopefully you enjoyed this video. It's kind of a fun synthesis that actually has something to do with biology and chemical biology as well as natural products and things you've smelled before. So geraniol actually gets its names from geraniums, and limonene gets its name from limes, and those are things that you've probably encountered and not even realized it before. So if you're enjoying Professor Carbon here, please do subscribe to our YouTube channel. We really genuinely do appreciate the subscribers. Seeing that number tick up slowly really helps encourage us to continue making these videos. If you're enjoying them so much that you want to get access to the PDFs of these questions, both before they're filled out and after they're filled out, you can become a patron subscriber, or you can just give us a like on your favorite social media account. Also, please share with your friends and feel free to watch the next video.